Okay, folks, here it is, the biggie, the fundamental theorem of calculus, or rather the second half of it, the one that we're probably going to use to find some areas or some definite integrals. So if you have a function that is continuous on some interval, so from a to b, and we're going to put it above the x-axis just so we can think about that integral. If we wanted to find that integral, so we're looking for the integral from a to b, definite integral of f of x dx, so area between the curve and the x-axis. It is equal to big F at b minus big F of a, which is sometimes written this way, big F of x from a to b. So what that tells us is that there's a relationship between big F and regular f. Like the derivative of the antiderivative gets us back where we started. And if you want to find an integral, you need to use the antiderivative. Another way to write the fundamental theorem of calculus, which is in some ways less helpful but more illuminating, is this. The definite integral of some derivative is just the original function at b minus the original function at a. What that hammers home is that differentiation, or slope finding, and integration, or area finding, are really the same problem come at from opposite perspectives. The fundamental theorem of calculus is right here, but the fundamental punchline of calculus is that even though this came from two geometric questions, they're really the same question from opposite perspectives. So that's pretty mind-blowing. But actually using it it's not that difficult. So essentially all we have to do is we have to find the antiderivative of whatever's here. So in this case, that's not hard. That's x squared minus 4x. And I'm going to use this notation and keep the 5 and 3. There is our big F, our antiderivative. And if I want to work this thing out, then all I have to do is do the antiderivative at 5 minus the antiderivative at 3. So if I put in 5, I'll have 5 squared minus 4 times 5. There we go. I'll put it in some extra brackets. The antiderivative at 3 is 3 squared minus 4 times 3. And I'll just work this through. So that's 25 minus 20 minus brackets 9 minus 12, or 5 minus negative 3, or algebraically we're going to get 8. I don't believe this for a second, so I'm going to head to the GDC. First I'll do it without seeing the graph, so I pressed math. I'm going to go for the definite integral. I'm going from, not from 0, but from 3 to 5 on 2x minus 4. Then it's got the dx there for me. It tells me the answer is 8. So if I trust my GDC, that's great. If I want to see the function, I'll type it in. I can graph it. And I can get it to work out this integral for me by pressing second, trace, and going down to the integral. And I tell it the left bound is 3, and that the right bound is 5, maybe a touch different on your GDC. And it will tell me that that area is 8. It says 8.000. On paper, too, I think that's how you'd want to do it. So the process is essentially antidifferentiate and sub in. Let's do the same thing for the next one. What's the antiderivative of e to the 2x? Well, it's going to be e to the 2x with a half out front. And if you're not sure, then you're going to check by differentiating. Let's check the derivative of 1/2 e to the 2x. That would be 1/2 e to the 2x from the chain rule times 2. Oh yeah, that'd get us back where we started. So we must have antidifferentiated correctly. Now that I've got that, I just sub in. So I'm going to do big F of 6, right? This whole thing is the antiderivative minus big F of 3. And I'll show every gory little step here. I'll show this as 2 times 6. But I think you probably just want to put that in as 12. And this will be e to the 2 times 3, or 1/2 e to the 12 minus 1/2 e to the 6. If for some reason you want to factor this, you could take out 1/2 e to the 6 and end up with e to the 6 minus 1, but I don't think that's really that useful. Or you can go ahead and find a decimal approximation in your GDC. So anti-differentiate and sub in. Let's try a few others. We know that when we have radical form, often we want to think of it in exponential terms. So I need to anti-differentiate. So the power goes up by 1, and 2/3 pops in front. Some people like to pop that 2/3 out front of the whole antiderivative. You can do that. I find sometimes it doesn't get distributed that well by everyone at the end. So I'm inclined to leave it in. But now, there's my big F of x, my antiderivative. I just need to go f, big F of 9, minus big F of 1. Okay? So that is 2/3 times 9 to the 3 over 2 minus 2/3 1 to the 3 over 2. Okay? And I threw this one in here to make sure that we remembered how to deal with fractional exponents. 9 to the 3 over 2 means square root 9, which is 3. Then cube it, so that is 27. And 1 to the power of anything is just 1. So this would be 54 over 3 minus 2 over 3, or 52 over 3 when we're done. So the last few that we've done have all been net positive. There's more area above than below. In fact, in this curve, everything's always going to be above. So feel free to pause and try the next one, or follow along with me. Again, I don't love the way this is written, so I'm going to write this in exponential terms without any fractions. And then I'm going to be careful as I anti-differentiate. So honestly, I'd probably do some scrap work over here. I'd go 4. Okay, power goes up by 1, and the flip of the new power comes down front. There we go. And then the other one, power goes up by 1, and the flip of the new power goes in front. Okay, so I think that my antiderivative is this. This is scrap work for me. And then I'm going to check it. So if I do my differentiation, that -2 times -2 gives me just 4. Power goes down by 1. This will become negative x to the minus 2. Okay, now I feel good about my antiderivative. And you don't need a plus c for a definite integral. It's actually not wrong to put it in there, but you'll just end up with the c subtracting out eventually. So this is from 1 to 4. And now I'm going to go big F at 4 minus big F of 1. And I'll be really careful as I put it in. -2, 4 to the -2, plus 4 to the -1. It might have been smarter for me to change that x to the -2 as an x squared on the bottom. That's okay, we can deal with negative exponents. We're tough. Plus 1 to the -1. So really carefully here, that's going to be -2 times 1 over 16 plus 1 over 4. That's all that first bracket. Minus, this will be -2 plus 1. Let's keep it in the brackets. That'll be -1/8 plus 1/4 minus -1. Or -1/8 plus 1/4 plus 1. And that'll work out to be 9/8. How confident do we feel about this? I mean, so-so. Let's head to the GDC just to make sure. A lot of the time, I don't really want to see the graph. I just want to work out this definite integral algebraically. So I've got a fraction of 4 over x to the power of 3. And then I have minus 1 over x squared. And dx, let's just see what we get. 1.125, that's 9/8. Yeehaw. One last one. I need to anti-differentiate cosine. I've got my little wheel of trig written down there. So anti-differentiate cosine, I get sine. Okay, so sine x between pi and pi over 4. And maybe I'll skip saying that it's f of pi here. I'm just going to sub it right in. Sine of pi minus sine of pi over 4. And the sine of pi is just 0. So that's 0 minus. The sine of pi over 4 is root 2 over 2, or 1 over root 2 if you prefer. Finally, we have an integral that is negative as an answer. Okay, so negative root 2 over 2, or you could write it as negative 1 over root 2. Either one's fine. But they're both exact. If you do it in your calculator, you'll probably get an approximation, which is fine too. For the last few questions in this video, we'll look at some ones that are set up in a sort of a less straight-ahead way. So this first one's saying find the area under one arch of sine 2x. So let me just graph sine 2x. Okay. If it had, that's just a rough sketch. If it had been sine x, this would have been 2 pi. But it's sine 2x, so it's going to be half as wide, or for one cycle. Or sometimes we say period is 2 pi divided by the coefficient of x, which is 2. The period would be pi. So one arch would be this area over here, from 0 to pi over 2. And in this question, we have to generate the integral ourselves. Okay, so the area is going to be this. The integral from 0 to pi over 2 on sine 2x dx. And I have to anti-differentiate. I know that the antiderivative of sine is negative cos x. Here it's going to be cos 2x. And because of that 2, I'm going to have a half here. Now I think you should probably take the time and just double check that that antiderivative gets you back to where you started if you differentiate. But it is. It's correct here. So now we just sub in. I'm going to go big F of pi over 2 minus big F of 0, where big F is this antiderivative we just found. Okay. So it'll be negative a half cosine of 2 times pi over 2 minus negative a half times the cosine of 2 times 0. Or negative a half cos pi minus negative a half cos 0. Okay. And the cosine of pi is negative 1. You can tell that just by looking at the unit circle. Okay, so negative 1. The cosine of 0 is positive 1, so this would be negative a half times positive 1. It's a lot of brackets here. But essentially, it all just works out to a half plus a half. Well, for all the weird units in this, this area is 1, which is pretty wild. Since it did ask us for area, we probably should say units squared in our answer. Though in math, the IB doesn't get too concerned about units. For 13, this looks really confusing. So, I mean, I've got some sort of function that looks like this. And essentially what they've told me is that between 3 and k, there is an area of 4. Okay, and they told us that k is greater than 0. It's actually true that there may be another answer somewhere back further that has a net signed area of 4. But they've told us here k is positive. So we can just set this up normally. We don't get too concerned that stuff is weird here. So it's just x squared from 3 to k equals 4. And then sub in. K squared minus 3 squared equals 4. k squared minus 9 equals 4, or k squared equals 13. And that gives us, when we square root, plus or minus root 13. But since k is greater than 0, k has to be root 13. Hard to imagine what exactly this looks like, so let's head to the GDC. There's the graph of 2x. I can go ahead and find this integral from 3 to root 13. So I'm going to type in root 13. And hopefully it's going to tell me that it's 4. And it does. It does tell me it's 4. So apparently this really does work if this value is root 13. Let's do one last question. We've got a function 1 over x that looks like this. We know that. And what we know is that the area from A to 5 is 1 unit squared. And I can say that it's 1 unit squared because this does not cross the x-axis. There's no passing between. Don't have to worry about net area. So what are we going to do here? Well, we're not going to get too concerned that it looks weird. Again, we're just going to take the antiderivative, which would be ln absolute value of x, from a to 5, and that's equal to 1. In other words, ln 5 minus ln absolute value of a, now we don't really need those absolute value terms because a is greater than 0, equals 1. You can solve this equation any way that you like, but I think it would be really nice to try and keep it exact. So from log laws, we'd have ln of 5 over a equals 1. And if we convert to exponential terms, that means we have a base of e, we'd have an exponent of 1 equals 5 over a. Or if we multiply, e times a equals 5, or a equals 5 over e, which you can get as a decimal approximation if you like, but there it is, just perfectly. Again, we can check this in the calculator. I'm not going to go down any sort of graphical rabbit hole. I'm just going to get it to figure this out for me using its definite integral function. And it's going to tell me 1, which is fantastic. So this is a big lesson. It tells us how to find those definite integrals, or those net signed areas. You antidifferentiate, and then you sub in. There's some practice on page 452, 454, and 566. I hope that you found this helpful. Good luck with the material, folks, and take care.